superimposition of various waves in the sine wave format, whether they're from light and the rest of the electromagnetic spectrum, or sound, or even water waves, will add together, mathematically additive, to produce new waveforms. And then that will lead us to the concept of beats, which is a phenomena that happens when you have two waves that are played at the same time and they have slightly different frequencies. And we have a demo for that. Okay, so sound is a form of energy that exists whether it's heard or not. You probably heard the line, if a tree falls in the woods, did it make a sound? Yes, it did. Because energy is produced, the waves are produced, they pass through the air, you get these compressions, you get rarefications, and the air waves through the air, the sound waves through the air will travel until the energy dies out and is transferred to heat eventually, and then the sound fades. Okay, so most sounds are waves produced by vibrations of matter, and that matter can be solids, liquids, gases, or even plasma. All right. Examples that you're well aware of are the versions of musical instruments. So in a piano, in a violin, guitar, any stringed instrument, the sound is produced by vibrating a string. You pluck the string, or in the case of a piano, you hit the key, which causes a hammer to strike the string inside the body of the piano, and you get vibrations of the string. And then those vibrations will lead to vibrations of the air surrounding it, and then that is heard as sound. In saxophones, you have a vibrating reed. You put the mouthpiece in your mouth, and this is a saxophone, any reed instrument. So a saxophone, a clarinet, an oboe, French horn, all of these have reeds or double reeds to them, and you're blowing, you're vibrating the reed, and then the reed will in turn vibrate a column of air that comes out, and you perceive that as sound. In the flute, you're directly creating a column of air in the flute. You're blowing into the flute. There's no reed there to vibrate, but the column of air through the length of the flute will produce various sounds. And in your voice, your vocal cords in your throat are vibrating, and you vibrate your vocal cords with air passing over them, and then that in turn vibrates air around it, comes out of your mouth, and that is your voice. All right, so the original vibrations, those primary vibrations that we just talked about, the ones you start the sound with, will often stimulate a second set of vibrations. Typically something larger, more massive, that will produce more sound, louder sound, amplified sound. And this could be the sounding board of a stringed instrument. So in the case of a piano, you have that little hammer hitting a string, and if that was it, it would just be ding, ding. It wouldn't produce much sound, but because it will vibrate the soundboard, the giant soundboard of the piano, it will create a resonance of the soundboard, and the soundboard in turn will be able to vibrate and produce vibrations in the surrounding air, which we will then perceive as sound. The column of air that, as I mentioned, from a reed instrument or a wind instrument. So reed instruments would be the ones I mentioned: clarinets, saxophones, oboe. Wind instrument, it contains all the reed instruments as well as flute. But also with brass instruments, the same thing: trumpets, trombones, tubas, French horns. There you're blowing into a mouthpiece. The mouthpiece may vibrate a little bit, but what you're really doing is vibrating the column of air that flows through these musical instruments. And the air in your mouth and throat are obviously secondarily vibrated after the vocal cords are vibrating to produce sound that comes out of your mouth. So the vibrating material then sends the disturbance through the surrounding medium. That's the air, generally. And that will, the air will be carrying that sound wave in the form of a longitudinal sound wave. Now, the initial sound waves, the initial waves that may have produced it weren't necessarily longitudinal. When you're vibrating a reed, it's actually vibrating up and down. That's more of a transverse wave, It's not really moving, but it's producing an initial wave. The air in the throat, that will be longitudinal. If you're hitting a drum, there's actually a waveform through the membrane of the drum. You can't see it, but you get a little circular sine wave spreading out from the drum head where you hit it, and that would be a transverse wave, kind of a two-dimensional transverse wave because it's spreading out in all directions through the drum head. So you can get other waves initiating these sound waves in the air, which then are longitudinal waves. Waves that involve compressions of air, followed by rarefactions of air, and then compressions of air and rarefactions as the wave is traveling. So the compressions and the rarefactions are happening in the same direction as the wave is traveling, as opposed to a transverse wave that is moving up and down or side to side as the wave is traveling along. So in a transverse wave, the wave movement is perpendicular to the wave, but in a longitudinal wave, the wave movement is actually these compressions and rarefactions that are parallel to the motion of the wave, actually along the length of the wave. All right, so under ordinary conditions, the frequencies of the vibrating source and the sound wave that they produce are the same. So generally, if something's vibrating and the air around it is affected by that vibration, the air will then vibrate with the same frequency, with some rare exceptions. We're not going to consider those in this course. But you have this vibration of some object, could be your vocal cords, could be the reed, and then that will set the air in motion with the same vibrational frequency. And therefore, the pitch will be generated from that frequency. And pitch is not necessarily a technical value that we can measure. We have names for pitch in music. We call pitches with different names, with different notes, A, B, C, D, E, F, G, with the do, re, mi system, do, re, mi, fa, sol, la, ti. And those are the pitches, and they have sharps and flats. Sharps would be a half step with a higher frequency, a half step up, or flat would be a half step down. That would be a slightly lower frequency. But these are perceived by our ear and our brain as pitch. So pitch is a subjective impression that happens in your brain of the frequency that's played. So frequency is an actual number that you can measure with an instrument, with a technological instrument, and give a specific number. This is the frequency, and then we would perceive that as a pitch, a high pitch, a low pitch, a medium pitch, etc. So the ear of a young person, I say young person because it deteriorates when you get older, like me, or if you have damaged your ears, like me. I used to be a drummer. I switched to congas to protect my ears. But I used to play drum set, and smashing cymbals next to your ears for a couple decades will take a toll on your high pitch, your high frequency hearing. But if you're young, your frequency range that you can hear is typically between 20 hertz, which is very low sounds, very deep, almost hard to almost pitches that you feel more than hear. 20 hertz, so that's 20 vibrations in a second. That sounds like a lot, but that's actually very, very small. It's very low frequency. To frequencies that are 20,000 hertz, and these will be the highest, almost like sounds that your ear can barely hear. And as you get older, we tend to lose our high frequency hearing, and that's because of the sounds we've been exposed to. It's also from natural aging, and that number will come down. In my case, I damaged my hearing from playing drums, so I have significant hearing loss after 2,000 hertz up to 20,000 hertz. But my hearing is pretty good below 2,000 hertz, and young people will hear high frequencies. In fact, you'll hear about devices that will produce a high pitched sound that only young people can hear, and older people like me or anybody pretty much over the age of 30 or even 25 will start to lose the hearing in the high frequency ranges, and that's normal aging. All right, so as we grow older, the limits of the hearing frequency range will definitely come down, especially at the high end. Occasionally you'll see it come up from the low end, but it more is affecting the high end frequencies. All right. So sound waves with frequencies below 20 hertz, these are ones we can't hear because they're too low. We call them infrasonic. Infra means below, so it's below sonic, the sound. It's below the sounds we can hear. And this is just like with light. We can see the visible range of light, red, the rainbow colors. So red all the way up to violet. Those are the colors of light we are able to see, and anything outside of that we can't see. With the wavelengths that are the frequencies that are lower than red, we call them infrared. You probably heard that term and not realized it literally means lower than the red frequencies. And on the other hand, we call frequencies of sound that are above what we can hear ultrasonic frequencies. I'm sure you've heard ultrasound. Well, ultrasound just refers to frequencies that are beyond the sound range we can hear. Just like we call the wavelengths of light that have frequencies above the color violet, we call them ultraviolet. And you've heard these terms many times and probably never realized that the words just mean below red, infrared, and above violet, ultraviolet. Well, the same thing goes with infrasonic and ultrasonic. It just means below the frequencies and above the frequencies that people can hear. So we just can't hear infrasonic, ultrasonic sounds by definition. They literally mean below the sounds we can hear in terms of frequency and above the frequencies that we can hear. So the words tell it all. All right. So sound waves, remember these are longitudinal waves. That means the compressions happen along the length that they travel. And they are vibrations in the air if it's traveling through air, if there are vibrations in other materials if sound is traveling through water or through steel, okay? And you get a mixture of compressions of whatever material it is for a moment, and then they spread out, and over here it moves, and they compress, and it's spread out. But it's not that they're moving. The material's not moving. It's just compressing in one place and then rarefying. That means expanding. And then the next area compresses and expands, compresses and expands. And that's how the wave moves. The energy of the wave moves that way until the energy is dissipated, usually in the form of just being lost to heat. And then the wave dies down. The amplitude dies down until it's nothing and there's no more sound transfer. So that's a sound wave. It's a longitudinal wave with compressions and rarefactions. All right. And it absolutely requires a medium that is made of matter. That could be solids, that could be liquids, that could be gases, that could even be plasma. But matter has to be there. There is no such thing as sound in a pure vacuum. If you've ever watched a science fiction story and they're out in deep space and some explosion happens and you hear, there is no sound. Now, if you're inside a vessel and you could hear it if you were inside another spaceship because the vibrations of the shock wave of force might hit your ship and vibrate it and cause sound, but the explosion itself would not have sound. So if you look at this, there's a little GIF here, a GIF. I always forget which way it's pronounced, but you can see the compressions. That's where it's very thick, where the particles are compressed together, and the rarefactions where it's expanding, and it looks like it's just continuously moving. That is the wave. Instead of being up and down, it's kind of thick and thin, thick and thin, thick and thin. And that is the movement of the wave. That is the movement of the energy. But the particles themselves are not moving except to compress and rarefy, compress and rarefy. But it's the wave that's actually moving, in this case from a tuning fork that has some specific frequency because it was designed to, when it's hit, to have a specific frequency that it might emit as sound. It might be like 440 hertz. That would be an A to people that do music. So a speaker is used to generate sound from electrical signals. If you're playing some music that came from a CD or an old album, something, it's being read by some device, and then that's converted to an electrical signal. Well, the way it creates sound in the speaker is that the electrical current has certain patterns in it, certain waves in the current itself, certain electrical currents, and that current is carried through a wire to the bottom of the speaker, in this case on the left side of the speaker. And what happens is the current, the wire that carries the current is actually wrapped around a magnet that is part of the speaker. The speaker actually has this cone, this wide part, that will vibrate and generate waves of sound in the air by it vibrating. It kind of pushes out, in and out, in and out in a very specific pattern. That will vibrate the air to produce sound we might hear as music or somebody talking. Well, how that's done is the fact that the electrical signals end up going through a curled wire that wraps around a magnet. Well, what we'll learn later in another unit is that when you take a current that's going around in a circle or a spiral, it generates a magnetic field. And the magnetic field will actually generate a current in response, but that magnetic field will affect the magnet that is literally glued to the bottom of the speaker. And what will happen is the current that's wrapped around the magnet, different patterns in the current, will actually make the magnet vibrate at specific patterns that mimic the music, and that will make the whole speaker move. It's very small. You can see it if you look at it. And that movement of the speaker pushes the air in very specific patterns to generate these compressions of air and rarefactions of air. And then the air will actually carry the sound wave as a longitudinal wave coming out of the speaker. And then that could be picked up by a microphone, and you could actually detect it. In this case, with a microphone attached to an oscilloscope, that's a scope that can read signals coming in from the microphone in this case, and you could actually see the waves of sound on a little screen, and you could determine the wavelength of the sound wave that's coming through. You could look at the frequency. The frequency is the how many whole waves happen in a second. The period is how many seconds it takes to make one wave. And you can measure that right off the screen. So you can use this if you really want to analyze it. But with music, it's actually more complex. So the waves are constantly changing in that case. All right, so air molecules will be set into motion, into vibration by the vibrating speaker, and that produces your compressions and rarefactions. That is your longitudinal wave coming out, and it will go out until it hits a microphone or it hits your ears, and inside your ear is an eardrum, which will be set to vibrate, and you'll get little waves in the eardrum. The eardrum will then be vibrating, and that will vibrate the bones on the other side of the eardrum, the bones called the hammer, the anvil, and the stirrups. If you're in biology, they're called the malleus, the incus, and the stapes. These are the three smallest bones in your body, 3 in one ear and 3 in the other. And these bones are then attached to your cochlea, which is filled with fluid, and then the fluid vibrates. There's actually waves through the fluid, so now it's more of a transverse wave that's flowing through there, and that will activate the hairs that are on the cochlea, and each hair is essentially assigned to different frequencies. So it will detect different frequencies and send signals to your brain that you detect as sound. Your brain will perceive it as sound, and that's how we hear, basically. All right, so sound requires a physical matter-based media, and okay, something elastic. Now we've talked about elastic, but in this case, any elastic material that can move and then move back, we're calling elastic. So that's solids, obviously, but also liquids, gases, and even plasmas can transmit sound as long as there could be some kind of vibrational movement and return to their original position. So in elastic liquids and solids, the atoms are relatively close together, so they'll respond very fast to each other's motion and transmit the energy with very little loss. And as a result, materials like this tend to transmit sound faster. Because when an atom is vibrating, it's right next to another to set the next one in motion. Now, I used to think this is because it's high density. High density actually makes sound go slower. The reason this happens is because of high rigidity, high elasticity. In other words, it's kind of stiff, so when it vibrates, it comes back to position very quickly, and therefore you can get a very fast vibrational response, a very quick response to the sound waves that are coming through it. So rigidity, elasticity in terms of rigidity is actually what makes the sound go faster. And in solids and liquids, that is much faster than we see in air. And you end up losing a lot less energy. In other words, the sound is transferred very efficiently. It doesn't die down as much through solids and liquids. And in fact, flowing through water, it's about 4 times faster. Sound moves about 4 times faster through water than it does through air. And this is kind of funny because when you study light, it's exactly the opposite. It's not 4 times, but light is slower through water than it is through air. But light needs no media, no matter to go through. So matter actually gets in the way for light and all the different wavelengths of the electromagnetic spectrum. But for sound, it gets faster when we have more rigid materials. Water is much more rigid than air is. And steel is far more rigid than water. So your textbook says sound travels about 15 times faster than in steel than in air. It's actually a little closer to 17 times faster, but it's the same ballpark. So it's much faster in steel, and that's because the atoms are held in place by these metallic bonds to each other, the iron and to a lesser extent the carbon that make up steel. Steel is about 99% iron and then a little bit of carbon in there. That's what turns iron into steel. And then people add other metals to it as well. You can have titanium and chromium and other metals added to iron to make it steel as well. But steel is mostly iron, and there are very rigid bonds that hold it together, and this rigidity makes them transfer their vibrations very effectively without a loss of energy, and the sound just goes through fast and efficiently. But rigidity of structure is not the only thing that affects the speed of sound. There are other things related to, say, weather conditions that will affect sound. They don't affect sound nearly as much as the rigidity factor that I just described. So these would include things like changes in temperature, changes in humidity, in other words, more water in the air, more water vapor in the air, or wind conditions. Now you can imagine wind blowing through past a sound wave will disrupt the sound wave. So we're not going to talk about that directly, but you can picture how wind would destroy a longitudinal wave going through the air. In terms of humidity, if we look at just dry, cool air, so this is air at 0 degrees centigrade, that's freezing point for water, and dry meaning the humidity is 0, there's no water vapor in the air. The speed of sound is 330 meters per second, about there. And that means that every second, the sound wave will travel 330 meters. That's about a third of a kilometer, okay? And that's a pretty good clip. It's moving very fast, but it's not nearly as fast as the speed of light. The speed of light is about 1,000,000 times faster than that. It's 300 million meters per second. All right. But the speed of sound is moving, and in humid air, in other words, you have some water vapor in the air, you find that the speed of sound is just slightly faster. Now, when I say slightly faster, even 100% humidity in the air only bumps up the speed of sound by about 0.35%. So we're talking about a third of 1% up in speed. It's a really small effect, but it just makes it a little bit faster. And the reason is when you put water in air, the water takes up some of the air. And water molecules, H2O, are just less heavy than O2 and N2, oxygen gas and nitrogen gas that are in the air, they're slightly less heavy, and as a result, they have slightly lower density. They make the air have a slightly lower density. Well, why is that good? Well, lower density in air, and if we only look at air, so I'm not comparing it to steel and water, within air, if I lower the density in the air for whatever reason, that means the mass that has to vibrate in this wave that's moving is a little bit lower. And remember, a sound wave is essentially energy traveling through the air. Well, energy in this case is in the form of kinetic energy. It's moving energy. Well, kinetic energy, we learned, is 1/2 mass times velocity squared. In other words, there's a mass term in there. The more mass you have, the more energy you need to make it go faster. But if you're not providing any extra energy, but you're making lower mass, you get to bump up your velocity a little bit. So lower density means lower mass, and because of the kinetic energy has to be constant, the velocity will bump up just a little bit because we're bumping down the mass just a little bit. And therefore we'll get it moving slightly faster in less dense material if that's the only thing we're looking at. If the only thing we're changing is density, it will go faster, okay? And warm air, because warm air is less dense, it's moving already, sound, it will also travel faster through warm air than cold air. And this will become important when we talk about refraction. Cold air slows sound down, and it actually slows it down a moderate amount. For every degree above 0 degrees centigrade, so anything above freezing in centigrade degrees, the speed of sound will increase by 0.6 meters per second. That doesn't sound like much compared to the 330, but if you're in a room that's 20 degrees centigrade, that's a typical room temperature, or you're outside in hot temperatures where it might be 35 degrees centigrade, 35 times 0.6 adds up and will bump up the 330 meters per second speed significantly. You might add another 10 or 20 meters per second to that, and that's a significant jump when you have warm air. So cold air, it's slower. Warm air, it's faster. Rigidity, we already mentioned, is actually a really big effect on sound. And so even though when you have liquids and solids, they're much denser, the rigidity is much, much greater. So it overcompensates for the extra density. So rigidity becomes more important. The density change, which would lower the speed of sound, is nothing compared to the rigidity increase, which will bump up the speed of sound. And that's why in water and in steel, we see these big jumps in the speed of sound. It's not just a few percent. It's 4 times in water. It's 17 times in steel. And these are giant jumps because of this increased rigidity of the molecules, so they can vibrate very efficiently and very fast and transfer their energy extremely well to make that wave move as fast as possible. Now, on the other hand, if there's no matter at all, as in a vacuum, sound can't move at all. There's nothing to vibrate. Sound absolutely requires matter to vibrate to start the vibration of the next matter to the next matter to the next matter. If there's no matter there, there is no sound, period. Okay? Nothing. So the speed of sound in vacuum is 0 because sound can't travel in a pure vacuum. And just to remind you, the speed of light, as I mentioned before, is 1,000,000 times faster than the speed of sound, about 300 million, 3 times 10 to the 8 meters per second. Just to give you a comparison, the speed of light is fast enough that if you shine a light and it could reach the moon, if there was enough energy to reach moon, it would reach the moon in about 1.25 seconds. Okay, but you'd have to wait 1,000,000 times that in order to have a sound wave reach the moon. And of course, it can't because there's no air there between the Earth and the moon, and therefore sound would stop entirely. But the rates of the speed differences are gigantic. All right, so if you watch a person chopping wood and note that after the last chop, so they're hitting the wood, you hear a sound 1 second later. How far away is the person chopping wood? About 350 meters. More than 350 meters, less than 350 meters, there's no way to tell. Well, remember I told you the speed of sound is 330 meters per second at 0 degrees. Well, at a warmer temperature, it might be 340, 350 meters per second. So let's say 350 meters per second because of the numbers in this question. Well, 1 second means it traveled 350 meters, somewhere between 330, 340, 350 in that ballpark. That's what sound travels on a normal day. And so the explanation is the speed of sound is about 350. If we're at, say, room temperature about 346. I'm rounding to 350. And there might be a little humidity, so that'll bump it up a tiny, tiny bit. We're going to round it to 350 here. So while we can see directly 1 second means 350 meters, because that's what the velocity says 350 meters per second. It literally is telling you how much it travels per second. Each second, 350 meters. Or if we had a different number of seconds, we could use the simple formula. We know that velocity is defined as distance divided by time. If we rearrange that formula, we get distance is equal to velocity times time. If you want to know how far something travels, it's the speed times the amount of time it went at that speed, and that's the distance. And if we plug that in, 350 meters per second times 1 second, seconds cancel, and we end up with 350 meters. And you can do this with any time and any velocity. All right, so let's look at the next problem. You hear thunder 2 seconds after you see a lightning flash. How far away is the lightning? Well, when you're near a storm, you're going to see the lightning first. Lightning is producing light, and light travels at about 300 million meters per second. Extraordinarily fast. So essentially, you'll see it almost instantly when the lightning happens. But sound travels 1,000,000 times slower. And depending on how far away from the storm you are, it's going to take some time to see. Remember, sound only travels about 350 meters per second, much, much slower. So you're always going to see the lightning before you hear the thunder. Remember, the thunder is just the sound that the lightning makes as it's cracking through the air. So you're going to see the lightning and then hear the thunder. The only time you're going to see the lightning and hear the thunder at about the same time is if you're right in the middle of the storm and the lightning is essentially right next to you. And then you'll hear it pretty much as you see it. But if you're any distance away, you will see it long before you hear it. So if it takes 2 seconds to hear it, how far away is the lightning? About 350 meters, about 700 meters, more than 700 meters. There's no way to tell. Well, we know that sound travels about 350 meters every second, meters per second. In 2 seconds, so it travels 350 in the first second, 350 in the second second. That is 700 meters. And that's again because of the speed of sound. Again, if we want to use the formula, distance equals velocity times time. We stick in 350 meters per second. We stick in 2 seconds this time, and we get a value of 700 meters. But you could just use logic. If it's traveling 350 meters per second, that means 350 meters each second. And there are 2 seconds, so that's 700 meters. As a general rule, because the speed of sound, 350 meters per second, is about a third of a kilometer. A kilometer is 1,000 meters per second. A kilometer is 1,000 meters, so a third of that would be about 333. 350 is close enough. So that's a third of a kilometer that it's traveling every second. So if you see lightning, count seconds as best you count, 1 1,000, 2 1,000, 3 1,000, slower than I just did. And whatever number of seconds you count, divide by 3, that's how many kilometers you are away from the storm. Divide by 5 if you want the number of miles you are from the storm, because it works out to about 1/5 of a mile. So reflections of sound. We have another name for reflections of sound. We typically call them echoes. But when sound reflects off of a wall, especially a hard, flat surface where the sound waves can bounce very cleanly off of it. We show them as rays here, but they're really waves hitting. And if that surface is rough or bumpy or has lots of pits in it from material, in other words, not wood or steel, something soft, something plush, something that gives a little bit and the sound waves hit it, some of those sound waves will be lost in the walls, the sides of the walls, or the carpeting, or the wall hangings, or the upholstery of your furniture, and you won't get clean bounces of waves. But if you have really sharp, flat surfaces, the sound waves can bounce extremely well. If you have multiple bouncing of sound waves off of surfaces, so it bounces off of one wall, hits another wall, maybe some hard furniture or a filing cabinet or something, multiple reflections, multiple echoes are called reverberations. So you're bouncing it more than once, even after the source has stopped. So the source can let out a quick sound and the sound can bounce around. And we know that from when we've been in giant rooms that have no furniture and no carpeting, hardwood floors or steel walls or concrete. We can hear echoes in a room when we just talk in a giant room that has nothing in it. It's always easier to hear those reverberations. You can just go, hello, and you'll hear hello, hello, hello inside a room. All right. So reverberations are best heard when you sing in a room with A, carpeted walls, B, hard surfaced walls, C, open windows, D, none of the above. Well, by now I think you know the reverberations, the reflections of the sound will happen better if you have a smooth, flat, hard surface that sound can bounce off of cleanly without getting lost in the material. So hardwood surfaces, rigid walls reflect sound easier. All right. The fabric is too absorbent. Open windows will let sound go right out and you'll lose some of the sound energy. And just think about the rooms you've been in. If you've ever moved out of a place and you packed up all your furniture and your rugs and your carpeting and your wall art and whatever could be interfering with sound waves bouncing around, suddenly when you leave the place in an empty room or when you're first moving in, you will hear the room echo much, much better. And that's because reverberations work much better. Multiple reflections off of walls work much better if the walls and the surfaces are very flat and hard and rigid. Okay, so here's another problem to consider. And this one's a little trickier. That's why it's in a different shade of green here. Consider a person attending a live concert that's also being broadcast over the radio. So you're sitting there watching a show and the person or you are sitting 45 meters from the stage, okay? It's about 150 feet away from the stage, right? And so the sound from the orchestra is traveling 150 feet to get to you, 45 meters to get to you, all right? At the same time, the person or you, whoever's listening, you have a transistor radio, and you've got the radio on your left ear, and you're listening to the concert live with your right ear. The question is, assume that the radio signal has to travel all the way around the world. In other words, some radio stations in there, they're picking up the sound and they're broadcasting it on the radio, and they're right up next to the sound. They're right up, the sound doesn't have to travel any distance. They're right up next to the sound, and some radio station is putting out signals, and the signals are electromagnetic waves. Radio waves are electromagnetic waves. They're not sound waves. And they have to travel around the entire planet Earth, which is 40 million meters around. So those waves have to travel 40 million meters to get to the radio that you're holding next to your left ear. Whereas the sound waves are right there and they travel directly to your right ear. So the question is, which sound do you hear first? The radio signal, the non-broadcast sound signal, in other words, the live signal right from the room, both at the same time, or none of the above? Well, you can't answer this by just looking and using basic logic. You actually have to use a little math. And remember, we're calculating the time of the radio signals, which go at one velocity, one speed, and the sound, the time of the sound that's going at totally different speed. As it turns out, they both arrive about the same time. And let's look at the math here. Electromagnetic waves of all kinds, okay? Visible light, ultraviolet, infrared, radio waves, microwaves, gamma rays, X-rays, they all travel roughly the same speed, about 300 million, 3 times 10 to the 8, meters per second, meters every second. That is incredibly fast. That's the speed it would take for light to go from Earth to the moon and back in about 2.5 seconds. It's crazy fast, all right? And it has to go around the Earth, 40 million meters, 4 times 10 to the 7 meters. Well, the formula for velocity or speed is distance per time. If we rearrange that and solve for time, it's distance divided by speed or velocity. Well, we know the distance that sound is traveling, 345 meters. We're 45 meters from the show. And sound is traveling 350 meters per second. Well, 45 divided by 350 is about 0.13 seconds, about 1/8 of a second. Light, which includes radio waves, has to go a much greater distance, but it's also much faster. It has to go 40 million meters, 4 times 10 to the 7 meters, but it's going at 3 times 10 to the 8, 300 million meters per second. Well, it turns out when you divide those numbers, you also get 0.13 seconds. They arrive at the same time. So you'll hear the radio sound in one ear and the real live sound in the right ear at almost the exact same moment. If you sat further back in the audience, you'd hear the radio sound before you heard the orchestra, and that would be very, very disturbing because it would be and everything would be a double sound to you. You go kind of crazy listening to a concert like that. And if you move closer than 45, you'd hear the live sound, and then you'd hear the radio sound. It all depends on your distance. We picked the distance where it would match. So reflections of sound, okay, so these are the echoes in a room, the reverberations in a room, and the study of this is called acoustics. And I know you've heard the word acoustics. It's just the study of sound, specifically sound bouncing around in a room and eventually reaching somebody's ear. So this becomes very important when people design orchestra halls. And I've been in orchestra halls that were designed extremely well, where no matter where you sat, you heard great sound from whoever was performing. But I've also been in halls where they made big mistakes. And there was a hall at the college that I went to that was famous because it was designed by a very famous architect, so it looked gorgeous from the outside, very unique from the outside. But unfortunately, the center of the audience, some of the best seats in the audience, had a dead spot where no sound came down and hit it. So you could be watching a show and barely hear the orchestra or the singer or whoever was performing on stage because sound wasn't reverberating to that position. It was bouncing around to all the other positions, but missing the center of the room. And everybody knew about it and it became a running joke, though. But you have to study where the reverberations are and what materials in the room will be absorbing the sound. Because you don't want totally hard, flat walls everywhere. You want kind of a mix. You want the sound to reverberate so that everybody can hear everything, especially in an orchestra that's very wide on stage, and you've got sounds coming from all directions. You want to make sure all those sounds get to anybody in any seat, but at the same time, you don't want those things reverberating forever because the person is trying to hear the next note. You don't want to hear the same note that was just played 5 seconds ago because the echoes are still going all around the room. So it's a real science and art to designing a room with the right acoustics so that everybody can hear everything and hear just enough reverberation to make sure you hear everything and make the sound full, but not too much reverberation that it just is a giant echo and it's meaningless sound that's coming to your ears. So some reflectors that are added, and you can see these reflectors hanging off the ceiling here, they're smooth, hard surfaces, but they're also curved to kind of spread out the sound to hit all of the people in the audience. But sometimes they make these reflectors so that they reflect light. They're almost mirror polish, and sometimes you can see light reflecting from the orchestra or from whoever's performing, as well as hear the sound waves. So both the light waves and the sound waves are reflected towards you, and it's a different kind of show when that happens. So acoustic designers have to account for everything. It's a very, very complex field, and it requires a lot of understanding of how acoustics works and how complicated the shape of a room will make any understanding of where the sound is going for every member of the audience. All right, so let's talk about refraction of sound. And like refraction of light, it's the bending of the waves. We'll talk about light waves in another section, but sound waves, like light waves, refract. They bend, and they can bend if it's going through one type of media and going into another type of media where the speed of sound changes. And if the speed of sound is getting slower, like going from warm air to cool air, it will bend towards the cool air. If it's going from cool air to warm air, it'll bend the other way. So it's always bending towards the cool air because the cool air has slower sound waves. And because you have different temperature variations every day and at different times of the day, you're almost always going to have refraction of sound outside. Remember, during a cool day or at night, the ground might be much cooler than the air above. And on a hot day, the ground will be much warmer than the cooler air above. So you can get all kinds of variations depending on the day, depending on the weather, depending on the time of day. But the cool air will tend to bend in the direction towards the slower area, which is cool air. So if you're in this top diagram, A diagram, the warm air is close to the ground because it's a hot air in the morning or hot air during noon, and there's cooler air above it. It hasn't warmed up yet. So in this case, if you blow sound, the sound will actually bend up, and somebody trying to listen to it at a distance won't hear the sound, or it'll be much more muffled because the sound waves will literally just go over their head. And that happens on warm days. But on cool days, if you create a sound, you've got a source. This is this figure B here. You create a source, and if the sound is even pointed up, the sound will be bent back down, and somebody listening on the ground will be able to hear pretty well. And in fact, this was what happens when you're out on a cool night. You'll frequently be able to hear better. You might remember times where you've gone out at night and it's cool out, and somebody speaks and you can hear everything, and you go, keep it down, because you can hear it better. This happens when you're out on a lake. The lake tends to be cool, and you might have noticed how you can hear everything when you're out on a lake. That's because the sound, instead of traveling up away from your ears, it gets bent back down towards you, and you hear somebody, half a mile away on the other end of a lake. It's remarkable how well you can hear when sound is bent back towards you and almost focused down towards you. And this is the refraction of sound. And this will happen with temperature variations, but it also happens with humidity to a lesser extent. Remember, humidity has a smaller effect on it, and wind could always disturb the sound waves, so that's always going to affect things as well, and just bend it just by virtue of blowing the air in a different direction. But temperature is one of the biggest reasons for refraction of sound. When air near the ground on a warm day, so the ground is warmed more than the air above, okay, you got cool air on the top, warm air on the bottom, sound tends to bend upward, downward, at right angles to the ground, none of the above. Well, it's always going to bend to the slower, cooler air. So in this case, that means it's going to bend upward. So sound travels slower as it moves from warmer to cooler air. Cooler air, it's slower. And this changes sound waves in the direction to bend upward. So the sound waves, if they're traveling this way, the wave is going this way. So we have the compressions are moving along. It's the compressions are happening technically perpendicular, but they actually are along the length of the longitudinal wave. So in the evening, when air directly above a pond is cooler than the warm air above. So you have a pond, you're out on a pond, you're in a canoe. It's really cool close to the water, and it's warmer up above. Sound across the pond tends to bend which way? Upward, downward, at right angles to the ground, none of the above. Well, if the lower air is cooler, it's going to sound that might start going up will be bent down towards the cooler air. And that's what makes it so easy to hear when you're out on a lake or a pond or whatever, some cool, flat body of water. The sound tends to be bent towards the cooler air because it's traveling. When it moves from colder to warmer, it speeds up. When it moves from warmer to cooler, it slows down. But as it's going up, it'll be bent down back to the cooler air. And so the sound waves will change direction. If you're going with the wave, we would write the waves perpendicular to the direction of the sound, but of course the compressions are actually happening within the longitudinal wave. And that's basically why it's easier to hear sound across the lake. If you've never experienced that, go out on a lake sometime and listen to sounds that somebody might be talking on the other end of the lake, and you'll be shocked at how good your hearing is when that happens. All right, so reflections and refractions of sound are frequently used in technical devices, especially ultrasonic devices like an ultrasound. We're all familiar with the ultrasound being used to detect structures inside the human body, especially when you're looking at a fetus growing inside a mother. And ultrasound can be used instead of X-rays because ultrasound is sound. It's sound that's too high a frequency for us to hear, but it's not damaging. It's not electromagnetic waves at high frequencies like X-rays, which are extremely high energy, high frequency waves of electromagnetic energy. That can be dangerous to tissue. That will actually break molecular bonds in human bodies. This is why we can't have too many X-rays. We'll do too much damage to our body, especially to our DNA, potentially increasing our risk of cancer. But ultrasound doesn't have that risk. It's not particularly high energy. It's nowhere near the energy of electromagnetic waves, especially X-rays or gamma rays. And this is why it can be used safely to look at pretty much anybody, especially mothers who have a growing fetus inside of them. And we can use this to look at structures because you have these reflections and refractions as it's going through different tissues. So within some tissues, it might be in a cavity and it bounces off inside the cavity, and that's a reflection, or against the outside of an organ and it bounces off. But some sound will go through, but as it's going through, it'll bend direction. It'll change direction because it's going through a new medium, maybe a denser medium or a less dense medium, or something that will change the speed of the sound and therefore bend its direction. And you have sophisticated software that can determine what kinds of reflections and refractions are happening, and from that information can recalculate an image. And this is how ultrasound is used. So high frequency sounds, which are not, there's a certain amount of energy to them because they're high frequency, but it's nowhere near damaging energy, what we call ionizing energy, like you have with X-rays that would actually damage the organs. And it'll reflect off the exterior of the organs, the interior of the organs, and go some will go through and bend, and that's the refraction as well as the reflection. And this is how we create these images. And so the images are dependent on the differing densities within the tissues, the different materials, different liquids. You'll have tissue and you'll have fluids, etc., and they'll all create these patterns that can be created, can be turned into an image by the software. And so any kind of complication in the tissue can be seen as a distortion of those images. All right, so humans aren't the only ones who use reflection and refraction of sound to gain information. There are animals like dolphins and bats and a lot of other organisms, some insects, that can emit ultrasonic sounds and perceive ultrasonic sounds. In other words, to them, it's not ultrasonic. To humans, it's ultrasonic. It's too high a frequency for us to hear, so it's beyond our frequency range for humans, but it's within the frequency range of these animals. And they can use it by sending out a signal. It bounces off the walls just like an ultrasound instrument would. It bounces off of other animals. It bounces off of different objects within the water and then comes back to the ear. In the case of bats, they send out signals. It might bounce off of an insect. It will come back to their ears and they will detect it and they will be able to track the movement of an insect. So various animals can use this kind of information extraordinarily effectively. It's called echolocation. They're literally sending out signals that bounce off, reflect, that, in other words, echo back to them, or they might refract and they end up hearing a reflection of a refraction. It's a combination of things, and they can use that to create images in their brain the way we create them from visible light, or how we create them with sound. We can imagine where things are with our sound. Animals that have this ability can create their images of where things are in order to view the world. All right, forced vibrations. So this is a situation where an object starts vibrating because something else near it is vibrating, and it will vibrate in response. And these are called forced vibrations. And so an example would be if you had a piece of heavy machinery sitting on a factory floor, and the machinery starts vibrating. Well, the floor is going to start vibrating too, usually at the same frequency. And then that will create enough vibration to make the air around it vibrate, and that will produce new vibrations and possibly even sound waves that we can hear if it's in the right frequency range. Car stereo subwoofer. These are the devices that produce those super low, heavy bass sounds that we've all heard people crank up in their cars. Unfortunately, a lot of people don't realize that those speakers that sound great to them and they use to, impress all their friends with, they're making the walls and the windows and the floors of the neighboring buildings vibrate, sometimes damaging them on occasion if they get strong enough. There's a strong enough amplitude and they start vibrating in sync with them, what we call resonating with them because of these forced vibrations. You can even feel it in your chest. If you go to a nightclub and you hear that heavy duty bass in there, you might feel it in your chest. Your chest is responding and starting to vibrate in response to the vibrations of the music that's being generated in the speakers. So a lot of objects have their own unique frequency that they will vibrate when set into motion, into vibration, and it's what's referred to as a natural frequency. It is the frequency that when something starts vibrating, it just vibrates at that frequency. And that is generally dependent on the size of the object, the shape of the object, and what the object's made of, the elasticity of the material. We have tuning forks that are designed the right length, the right thickness, and the right shape in order that when they're hit, they always make the same frequency sound. And we might perceive them as the same musical pitch. That will happen, they're designed that way on purpose. When you pluck a guitar string, it is designed to have a specific frequency that will be perceived by our ears as a particular pitch, a particular musical sound. And that is typically based on the length of the string and the thickness of the string as far as what that vibration is. And it might be even a multiple of vibrations that can be perceived as a collection of pitches in our ear. The tuning fork, for instance, the 440 tuning fork, that's a tuning fork where you hit it and you just have to smack it once and it'll start vibrating with a vibration of 440 vibrations per second, 440 hertz. So the phenomena in which the frequency of forced vibrations on an object matches the object's frequency, natural frequency. In other words, you start vibrating something and it matches the natural frequency of something else, the other thing will start vibrating. I'll give you a weird example. I've gone into public restrooms And just from talking to myself, I've noticed that certain pitches will make the walls or the doors move of the stalls. And then I started playing with different notes, and I realized if I sang a certain note, I could actually make the walls start vibrating. And if I hit the next octave up, which is double the frequency, it'll vibrate again. But anything in between, it won't vibrate. It's not the natural frequency. And this happens with a lot of different objects. And so when you get one object to vibrate because you happen to be vibrating one thing at the natural frequency of the other thing, the other just start vibrating in response because it's making a vibration. That vibration causes air to vibrate with the same frequency. And when that air hits the second object, if that object likes to vibrate at that same frequency, it'll start vibrating. And that is the concept of resonance. So there are some things that aren't even sound that will hit a natural frequency. If you've ever pushed a child in a swing set, they don't go super fast or super slow. There is a set speed that child will swing based on the length of the pendulum and the gravity of Earth. And that will be the right speed, and you'll just be pushing the kid at that speed, going back and forth, and they will be going so many times back and forth every minute, and you would have a natural frequency of that swing. It's because that's really a pendulum. You can also get resonance in the case of speakers. People have done this where they used to do this in commercials where somebody would sing and they'd amplify the sound and break a glass. A company called Memorex that used to make tapes, sound tapes, would do this. And what you can do is if you blast a sound from your speaker that happens to be the pitch that is the natural frequency of a glass. So a glass has a natural frequency. You might be able to find it by just clinking the glass and hearing that pitch. And if you blast from a speaker that same frequency of sound, but really loudly, it'll vibrate, the speaker will vibrate the air at a certain frequency, and that frequency of air will hit the glass and it'll start vibrating the glass. And if it vibrates it with a high enough amplitude, with a high enough energy, the glass will vibrate so much it'll shatter. And that's what these pictures show here. And resonance actually becomes very important when you have large groups of people walking across bridges. Bridges have a structure to them. They're across some body of water typically. And because they have this long length and they're made of materials, they have their own resonance frequency. And unfortunately, sometimes moving across the bridge with a lot of people or cars all producing a certain vibration on the bridge at the same time, if that vibration matches the natural frequency, the natural preferred vibration of that bridge, you start making the bridge move in ways it was never meant to move. And so when military groups are walking across the bridge, they will break formation as they go across the bridge in order to not activate these resonance frequencies of the bridge that might end up making it sway or move up and down or move up in a wave form and would literally tear the bridge apart. And this sort of thing has happened. Now, in a lot of introductory courses in physics, especially with older textbooks, you might find this as an example of destructive resonance. This is the Tacoma Narrows Bridge, which was destroyed in 1940, soon after it was built, and wind induced the bridge to start resonating with its natural frequency. But it is now believed that this was probably not what caused the bridge to actually just be destroyed and twist apart, because what ripped the bridge apart was a twisting motion, which was probably not due to normal resonance frequency of the bridge. It was actually due to the fact that the sides of the bridge were solid walls and they blocked the wind, and it resulted in this twisting motion that ultimately ripped the bridge apart. So we're not going to count this as an example of destructive resonance. There was resonance there, but it probably wasn't what destroyed the bridge. However, In the year 2000, there was another bridge in London called the Millennium Bridge, named for when it was built. The new millennium would have started January 1st of 2001. And what happened was when they opened up the bridge in 2000, people all wanted to come across the bridge. Thousands of people started walking across the bridge. And just that walking across the bridge started moving the bridge, and it started swaying. And as people were walking, because the bridge was swaying, people would change their gait of motion to match the swaying of the bridge. And as they did that, in order to keep their balance, it increased the swaying, it reinforced the swaying, and the bridge was almost at the point of collapse. But luckily, they got everybody to stop. They got everybody off the bridge just in time. And then they shut the bridge down for a while and rebuilt reinforcements on the bridge to prevent it from doing this twisting and swaying, and actually ended up saving the bridge before any real damage happened. So it was a success story, but engineers are much more wary of how they build any bridge to avoid any kind of resonances, whether they're created by wind or other natural phenomena, or by the feet of people just walking across the bridge. All right, so interference. We've talked about interference before. Interference is the property of when you have more than one wave happening simultaneously. You just mathematically add up the wave structure. So positives are added to whatever the second wave is. It might be positive or negative, and you add them up and you get some mathematical construction of the two. And if the two waves are what we call in phase, in other words, the troughs, the peaks, called crests, and the troughs, the bottom part, match between two waves, you'll get reinforcement. The crests will go higher, the troughs will go lower, and you'll just end up with a bigger version, this reinforcement on the left here. But if the waves are completely out of phase, in other words, when you have the crest of one wave, if you look at the same time, it's the trough of the other wave, and then vice versa. When they add together, you end up getting the wave completely canceled out. The sum of the two cancels out, and you'll see this when you do your problem sets. So that kind of cancellation is a negative interference, a negative interference pattern, whereas the first one is a positive interference pattern, or a constructive interference pattern. So the first one's also called constructive interference, and the second one's called destructive interference. You're losing the waveform. All right, so interference is a property of sound, light, both, or neither. Well, interference, as we learned in the last unit, is a property of any kind of wave. It could be sound wave, it could be anything in the electromagnetic spectrum of light type waves, radio waves all the way up to gamma rays, including visible light, etc. It could also be water waves. They can add together. If you have waves of water coming at each other from different sources, they will add together, sometimes constructively to make higher crests and deeper troughs, or destructively to make it all flattened out. So it's both. Any kind of wave can have interference if you have two or more of those waves coming together. So interestingly, the presence of interference actually tells a physicist whether something is wave-like. If you see interference patterns, it lets you know that there must have been waves. And actually, one of the ways light proven to be a wave was by these interference patterns that couldn't be explained in any other way. So interference patterns, we showed similar diagrams in the last unit. You can have constructive interference where you're making the troughs higher and the crests higher and the troughs deeper. That's constructive because the waves essentially look similar and they add together or subtract together on the other on the troughs, and you get much bigger versions with higher amplitudes as a result. But you can have destructive where they kind of cancel each other out. You get one wave that's essentially the negative version of the other wave. And so here are some diagrams that show you two versions of constructive interference. These are the A and B, and two versions of destructive interference, C and D. The difference is the first and the third are transverse wave versions of interference, and the second, B and D, and the fourth, the D, are examples of longitudinal waves that are undergoing interference. So those have compressions and rarefactions. And you can see in A, if you add two similar waves that are right on top of each other, you end up with a bigger wave. If you do this in B with a longitudinal wave, you have compressions and rarefactions, and you add them together, you get bigger, deeper compressions with more particles in there, and your rarefactions are even more rare as far as the particles. So it's even more spaced where you have particles that are dense in repeating areas, and then you have not dense areas in between there, very sparse areas where there's very little matter vibrating. And then likewise with C and D, you can see in C you have destructive with a transverse wave, and you end up with adding the waves together, you'll end up with a no wave. They completely cancel each other out, because everywhere there's a peak in the left wave, there's a trough in the right wave, and when they add together, you get nothing. And then the counter example to that would be the longitudinal wave, where you have rarefactions and compressions that are not matched with compressions and rarefactions of another wave. When you add them together, it's just as if there was nothing happening, just the air or whatever object was having the sound wave go through essentially had no compressions and no rarefactions. All right, so this can happen with sound interference as well. And as I mentioned before, sound interference in a destructive interference pattern can actually be used for good. In the case of instruments of construction or anything that produces a large amount of sound, if you have another source of sound that produces sound waves that are exactly mirroring the sound waves from some loud, annoying instrument that's causing a lot of noise damage to whatever, if you produce a mirror image of that as quickly as you can to match the original sound, you'll end up essentially destroying the two waveforms. They'll match each other and cancel out, and you end up with a very flat wave that essentially means there's almost no sound. And people do this with loud construction devices like jackhammers. They might have a microphone picking up the sound, and then a speaker producing the negative version of that, the mirror image of that sound, and canceling out the jackhammer. They're not going to be perfect because there's always a lag of trying to the technology trying to figure out what was just played and producing that sound quickly enough to match it, especially if the other sound is changing its pattern as it goes. But these are at least partially effective to lower the overall amplitude of sound. And so this is actually what's referred to as noise cancellation technology. All right. So sound interference can also be seen without anything special. If you take two speakers that are producing similar sound from your stereo and you turn the speakers towards each other, they're producing waves, but they may not have exactly the same sound coming out of one as the other. And in doing so, if they're slightly off from one another, their waveforms are rarely going to have crest here and crest here. It might be less than a crest over here, and this might be a trough here, and there might be a crest over here. They're not going to be exactly the same, and so they're going to partially cancel each other out. So if you put the speakers close to one another facing each other, the sound waves will add together, and in many cases will actually flatten out the patterns, because one sound from one speaker is producing something that partially cancels the sound from the other speaker, and you'll end up with just a lower volume sound because some of that amplitude of the waves is shrunk down to a less amplituded wave. I know that's not really a word, but a smaller amplitude wave in response. So you can actually do this yourself. All right, so beats, this is the last topic we're going to cover, and this is really an interesting topic of acoustics. It turns out that if you have two pitches playing that have not identical frequencies, but really close to the same number frequency, so one just slightly different from the other, and if you start playing these two sounds, so in this diagram we have two tuning forks here, tuning forks, and one has a pitch of one frequency and one has a pitch of a slightly different frequency. And what happens is to your ears, you're going to add those waveforms together when you hear them, and something very interesting happens as a result from this interference pattern due to the superposition of the two waves. In other words, the mathematical adding of the two waves that your ears perceive. And so you see, if we have the bottom wave and the top wave, we add them together, you'll notice there are areas where they're doing the opposite, a rarefaction where the particles are spread out, and a compression from the other wave are happening at the same moment. Well, they're going to cancel each other out. So in red, we've got areas where the two waves are doing the exact opposite. And those will cancel out, and you end up with a very flat area with not much sound. Whereas in the constructive areas, when those frequency waves are matching each other, when the compressions match and when the rarefactions match, you'll end up with higher than usual amplitudes and low, and so you'll end up with higher crests and higher crests and lower troughs. So you get a wider amplitude in those areas, and these tend to repeat one after the other, where you have destructive, constructive, destructive, constructive, alternating, and you end up creating a new complex wave that has a very specific pattern. And so this allows people to make comparisons between two similar frequencies in order to determine if they're the same or if they're slightly different. Because if they're slightly different, you'll get this weird constructive, destructive, constructive, destructive alternating pattern in the new sound. And this rhythmic wavering of the loudness of the sound is referred to as beats. Now, you've probably heard beats. I'm sure you've heard beats with other uses, but there are acoustic beats. These are a new version of sound that will have a new frequency that turns out to be exactly the difference between the other two frequencies. So if one was 440 and one was 444, the beats will have a frequency of just 4 hertz. Okay, the difference between 444 and 440. I hope I said those two numbers. The difference between those two. So whatever it is, as long as they're close, you'll hear those beats, and you'll hear this wavering of the sound over top of the other sounds. That's the result of this constructive, destructive, alternating interference. And so below here are examples of what this wave pattern actually looks like. So we have 3 different waves here. The top 2 are the original waves. So somebody hits a tuning fork and it has a certain frequency and it's making this waveform, and then that's the purple one at the top, and then somebody hits another tuning fork, and so they're both sounding at the same time. We have the red frequency, which is slightly faster frequency than the purple one. Not that different, but slightly different, a little faster. Well, it turns out, if you look at this, you'll be able to hear these, because when you add these two together, you get this blue pattern, which is kind of complex. You can see these waves still happening, similar frequencies of the originals, but what you also see is they completely destruct at one point, and then they construct, they reinforce to make bigger versions of the waves, and then they come down to nothing, and then they get bigger, and you end up with this new repeating pattern that has a totally different frequency, which is much slower than either one of the two that it came from. And people use this to tune instruments. They will actually play a tuning fork. If they're trying to tune a piano, they'll hit a tuning fork that has a very specific frequency, and they'll hit the piano key that's supposed to match that. But if it's different, you'll get this interference pattern that you'll hear instead of doo, doo, the same pitches. When they come together, if they're a little off, you'll hear woo, 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 and that is due to the beats. And the same thing is done when people are tuning an orchestra. If they use the piano or they use the oboe, they'll play a pitch and everybody else is trying to match it. And if they're not matching it, you'll hear this wavering sound. So the frequency of the beats is always whatever the frequency of the two individual ones, and you take the difference, and it's whatever the positive version. It's never a negative number. So you take the bigger number minus the smaller number, and that is the frequency of the beats that are formed. It's a sound that's generated because of this interference pattern. So I'm going to play for you a little demo, and this demo is actually by the author of the textbook. So he hits 2 tuning forks here.
So they're a little bit different in strike them both at the same time.
Hear that?
Can you hear the throbbing?
Hear the
That is the result of interference, and the phenomenon is called beats.
So that's what beats sound like. And with that, we'll end here.